April 17th, 2026. A team of engineers at NASA's Jet Propulsion Laboratory sends a command into deep space. It travels at the speed of light. It still takes 23 hours to arrive. When it does, a scientific instrument that has been running almost without interruption for 48 years goes dark forever. Voyager 1 is dying. The most distant object ever built by human hands is running out of power. 7 of its 10 instruments are already gone. 2 remain, and NASA has one last desperate fix that could either save the mission or end it permanently. They are calling it the Big Bang. This is Voyager 1's final chapter. To understand what we are losing, you need to understand what this spacecraft actually did. September 5th, 1977. A Titan Centaur rocket lifts off from Cape Canaveral, carrying 815 kilograms of hardware, designed to last 5 years. The Centaur upper stage nearly failed before the mission started, running out of propellant with just 3.4 seconds to spare. It did not fail, and 18 months later, Voyager 1 arrived at Jupiter. 9 active volcanoes erupting simultaneously on Io, the first volcanic activity ever discovered beyond Earth. A faint ring around Jupiter invisible from any telescope on Earth. 2 previously unknown moons. A single flyby produced discoveries that centuries of ground-based observation had completely missed. Then Saturn, November 12th, 1980. Thousands of individual ringlets where scientists expected a simple disk. Titan's atmosphere revealed as 90% nitrogen with complex hydrocarbons, mirroring the chemistry of early Earth. That Titan flyby kicked Voyager 1 out of the plane of the solar system forever. No more planets, just open space. And in February 1990, 6 billion kilometers from home, Carl Sagan convinced NASA to turn the cameras around one final time. Earth appeared as less than a single pixel, a pale blue dot in a sunbeam. Every human being who ever lived reduced to a fraction of a point of light. Then the cameras went dark to save power. Voyager 1 kept going. August 25th, 2012. 35 years after launch, instruments recorded an 80-fold jump in electron density. The solar wind vanished. Galactic cosmic rays flooded in. Voyager 1 had crossed the heliopause and become the first human-made object in history to enter interstellar space. A spacecraft built for 5 years had been flying for 35, sending data from a place nothing built by our species had ever been. Here is the physics of what is killing Voyager 1. The spacecraft runs on 3 radioisotope thermoelectric generators, RTGs. They convert heat from decaying plutonium-238 directly into electricity. At launch, those RTGs produced 470 watts, enough to power everything simultaneously. Plutonium-238 has a half-life of 87.7 years. The thermocouples that convert heat to electricity degrade independently on top of that. Combined, these 2 effects drain the power budget at approximately 4 watts per year, every year, without stopping, without any way to reverse it. After 48 years, available power has dropped below 230 watts, less than half the original output. And here is the nightmare scenario. Without heaters running, the fuel lines connecting to Voyager 1's attitude control thrusters freeze solid. If those lines freeze, the spacecraft loses the ability to point its antenna at Earth. The signal stops. Not because the transmitter fails, because the spacecraft cannot hold the angle. Every power decision is a razor-edge calculation performed across a 23-hour, one-way communication delay. Engineers send a command from Pasadena, 23 hours to arrive. Another 23 hours for confirmation to return. 46 hours of waiting to know if anything worked. NASA planned for this long before it became critical. Years ago, the science and engineering teams built a pre-agreed shutdown list. Each instrument evaluated for scientific value against power cost, ranked in order of sacrifice. 7 of the 10 instrument sets are now permanently dark. The cameras went first in 1990 after the pale blue dot. The ultraviolet spectrometer, the photopolarimeter, the infrared instrument. Each shutdown buying months of additional life for what remained. In February 2025, the cosmic ray subsystem went silent. 3 telescopes that had been measuring high-energy particle populations in the interstellar medium almost without interruption since launch. Gone. Then on February 27, 2026, during a routine roll maneuver, power levels dropped suddenly. The spacecraft's undervoltage fault protection system, designed to automatically shut the probe into safe mode, nearly triggered on its own. Engineers watching the telemetry saw exactly how close the margin had become. They made the call. April 17, 2026, the shutdown command is sent. 23 hours later, it reaches Voyager 1. 3 hours and 15 minutes after that, the low-energy charged particles experiment goes offline. An instrument measuring ions and electrons streaming through interstellar space, running almost without interruption for 48 years, goes dark for the last time. Kareem Badaruddin, Voyager mission manager at JPL, described the decision plainly. While shutting down a science instrument is not anybody's preference, it is the best option available. 2 instruments remain: the plasma wave subsystem, which listens to oscillations in the electron density of the interstellar medium, and the magnetometer, which measures the magnetic field threading through interstellar space. 2 instruments on a 48-year-old spacecraft, in a region no other human-made object has ever reached. Here is the move NASA has left. Keeping Voyager 1's thruster fuel lines from freezing requires heaters. Those heaters consume power that could otherwise run the remaining science instruments. If engineers can accomplish the same thermal protection using 10 fewer watts, they extend the mission by at least 1 year. There is even a chance of temporarily switching the LECP back on. The plan: shut off 3 devices currently heating the thruster lines. Switch on 3 different devices that accomplish the same thermal goal while consuming approximately 10 fewer watts. 10 watts. On a spacecraft running below 230 watts total, 10 watts is the margin between life and death. But the risk is severe. Every heater system still operating on Voyager 1 is single string. No redundancy, no backup. Suzanne Dodd, Voyager's project manager, described it directly. Everything on board is single string. One failure in the wrong place and there is no workaround. The procedure involves switching off systems that have run continuously for years and activating systems that have been dormant. In temperatures approaching negative 270 degrees Celsius, barely above absolute zero, hardware that worked in 1977 may not respond the same way in 2026. So NASA tests it on Voyager 2 first. Voyager 2 entered interstellar space in November 2018 and carries slightly more power. Tests are planned for May and June 2026. If successful, the same procedure will be attempted on Voyager 1 no earlier than July 2026. The command is sent. Engineers wait 23 hours for it to arrive. Another 23 hours for confirmation. 46 hours of silence before they know if it worked. If it fails and the fuel lines freeze, the antenna drifts. The signal stops. 25.8 billion kilometers from the people who built it, Voyager 1 goes permanently silent. Voyager 1 is the only instrument humanity has ever placed in interstellar space. When it goes dark, no replacement is coming soon. A spacecraft launched today would take approximately 35 years to reach the heliopause. Scientists would not see another direct measurement from interstellar space until the 2060s at the earliest. The data from the two remaining instruments is irreplaceable. The plasma wave subsystem has detected a persistent low-level hum in the interstellar medium, evidence that the space between stars has structure, turbulence, and density variations no model fully predicted. The magnetometer is measuring the interstellar magnetic field physically, in place, in real time, from inside interstellar space. That data is being collected nowhere else. In a 2025 blog post, NASA projected that the sequential shutdown plan could keep at least one science instrument running into the 2030s. Every decision the team makes, every watt conserved, every heater recalibrated across 23 hours of signal delay is aimed at that single goal. When Voyager 1 finally goes silent, it will not stop moving. At 17 kilometers per second, it will continue outward into interstellar space indefinitely. In approximately 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445. It will not stop there either. Attached to its frame is a gold-plated copper disc, the Golden Record. 115 images of life on Earth. Whale song, rainfall, laughter, greetings in 55 languages. 90 minutes of music from Bach to Beethoven to Chuck Berry. Instructions for how to play it encoded on the cover. It was assembled under one assumption, that Voyager 1 might someday be found. Not a certainty, not even a probability. A possibility taken seriously enough to act on. Because the universe is old and vast, and we do not know everything it contains. A spacecraft designed for 5 years. 48 years later, it is still out there. Still transmitting, still exploring a region of the universe no human instrument has ever reached. This summer, engineers in Pasadena will send one more command into the darkness. They will wait 23 hours, and then they will find out if Voyager 1 has one more chapter left. Whatever happens, the Golden Record keeps moving. Through 40,000 years of stars, carrying every sound of a world that pointed a spacecraft at the sky and refused to stop listening. If this story moved you, hit the like button and subscribe. Every fact in this video comes directly from NASA's official JPL documentation and peer-reviewed research. All sources are in the description.